Hello everybody and welcome to this next video about GCSE chemistry, and today we're going to be looking at an important topic, concentrations of solution. Now the reason this is important is because so many chemical reactions actually happen in solution. And what we're going to cover in this topic is what a solution actually is, what we mean by concentration, then we're going to move on to talk about how we can calculate concentration, and then related to concentration we're going to try and calculate the amount of solute that is in a solution. Then we're going to move on to looking at converting the different units that there are for concentration. There are two different concentrations, of two different ways of describing concentration. And we're going to finish off looking at something called uncertainties, which is what you get whenever you make a measurement in an experiment. First of all, we're going to look at solutions and what they actually are. The reason I'm doing this is that it's quite confusing because there are three words and they all sound really similar. So we've got the word solution, we've got another word which is solute, and another word which is solvent. And so if we first of all tackle the word solute, solute is the thing that is going to dissolve. Now, usually that will be a solid, but occasionally it can be a liquid as well, because sometimes one liquid will dissolve in another. And so the solute is going to dissolve in something. The thing that it dissolves in is the solvent, and that is a liquid. So the solvent is the liquid that the solute will dissolve in. Now the reason that I've drawn two beakers of solvent is I'm going to put one of my solute clumps into the solvent. And when the solute dissolves, what happens is the particles of solute split apart and they break up and they spread out into the solution. They are all spread out there. And so the solvent surrounds the solute and together they make a solution. And so that's the third of these words. So the solute is the thing that is going to dissolve, the solvent is the liquid that the solute dissolves in, and the solution is what you're left with once the solute has dissolved in the solvent. And so really common examples of these types of solution, we get salt water, so the C has got sodium chloride, salt dissolved in water. Coffee, even more every day. The coffee is the solute. When you pour hot water on it, that's the solvent, and the liquid that you drink is the solution of coffee. And a more chemistry lab based solution is copper sulfate, which is a blue solution that you can turn into crystals. If we start to think about the word concentration now, what the word concentration means is it is a measure, so it's always a number, it is a measure of the amount of substance that is present in a certain volume. So the amount of substance in a certain volume. Now the best way to introduce this as a concept is to think about something that we consider more often than we talk about the chemistry of it. And so if we consider this bottle on the left hand side and we say that this bottle is a bottle of orange squash. Now this orange squash, we might describe it as being very concentrated. And then if we take some of that orange squash and we put it into a glass, maybe up to this level on here, and then we turn on the tap and we add some water to it, and we bring the level up to a higher level up to the top on here. So we've got some of our orange squash, and we've got a lot more of the water on here. So we've added a lot of water, and we've got some squash in there. And obviously that then all gets mixed up to make a glass of orange squash. And the word that we use to describe the orange squash is we say that it is dilute, or we say we have diluted, but dilute is how you would describe the solution. So the diluted solution has got fewer particles of orange squash per unit volume. So if we zoomed in on a little bit of that orange squash there, then we would see that we've got very few particles in this particular volume. If we zoomed in on the same volume of the concentrated orange squash, we would see that we have got more particles. We don't need to worry about how many more, but we've definitely got more particles in the same volume. Now, I've just been using the word volume there, so I think it's important that we take a moment to consider what volume actually is. So volume is an amount of space that something occupies. And because space is in 3 dimensions, we always talk about a cubic volume. And so what's on the left-hand side here, this cube that I've drawn, I'm going to say that this is 1 cubic decimeter. And so we write 1 dm cubed, but that is 1 decimeter cubed. Now, what a decimeter cubed is in day-to-day talk, it's actually 1 litre of space, but in chemistry we need to call it a decimeter cubed, and deci means 1/10 of something. Now, more commonly day-to-day we might use the word centimetres or cubic centimetres or centimetres cubed. Now, those are much smaller volumes on here, so this would be 1 cubic centimetre on there. And so a centi is 1/100th of something. And so if we considered a particular volume, I'll draw my 1 cubic decimeter again. So if we were to label that, that would be 1 decimeter in that dimension, another decimeter in this dimension, and another decimeter in that dimension. So the volume of my cube that I have drawn is 1 times by 1 times by 1, because that's how you work out volume. It's this dimension times by this dimension times by the 3rd dimension, which is nice and easy here, 1 cubic decimeter. If I substitute and change that from being 1 decimeter to have it being 10 centimeters, because they are equivalent, 1 decimeter is 10 centimeters, and so the same size cube, if we consider centimeters instead of decimeters, would have dimensions of 10 centimeters times by 10 centimeters times by 10 centimeters, which of course 10 by 10 by 10 is 1,000 cubic centimeters on there. So that would be the same volume. We would just have different units for that exact same volume. Since we've got 2 different units for volume, we need to be able to convert them from one to another. And so on the left-hand side, I've just drawn a small cube, 1 centimeter cubed in size, and on the right-hand side, I've drawn a cube that is 1 decimeter cubed in size. Now, they're not quite to scale, but they're representative. So since 1,000 cubic centimetres is the same as 1 cubic decimeter, to convert between the two, we just either need to multiply or divide by 1,000. So we've got an example here where we've got 3 cubic decimeters, and I want to turn that into cubic centimetres. Since 1 cubic decimeter is much bigger than a cubic centimetre, we're obviously going to be multiplying by 1,000 as we go this way. So 3 cubic decimeters is 3,000 cubic centimetres. 0.2 cubic decimeters, again, we're going to multiply this number by 1,000, and that's going to be 200 cubic centimetres on there. If we're going the other way, it makes sense that we do the opposite function. So instead of multiplying by 1,000, we need to divide by 1,000. So 2,400 cubic centimetres, we divide that by 1,000, and we get 2.4 cubic decimeters. And last of all, 370 cubic centimetres, we divide that by 1,000, and we get 0.37 cubic decimeters. Now we've looked at volume, we need to move on to look at the units that concentration might have. Now, what they all have in common, whatever the 2 units are, is that they are an amount of a particular substance per unit volume on there. And so the 2 different units are either going to be a mass per volume, that's an amount of substance, of course, mass, and if it's going to be in mass, it will probably be in grams, and the volume, as I've just been saying, is most likely to be in decimeters cubed. So we would say grams per cubic decimeter. That divide by symbol, in terms of what we would say, we always say per on there. The alternative units, instead of using mass, and another method of measuring the amount of a substance is in moles, and so moles per unit volume on there. And the units for moles divided by volume is very logically mole for moles and volume once again in cubic decimeters. So we would say moles per cubic decimeter on there. If we consider now in a bit more detail mass per unit volume, we can explain that by an example. And so if we take 40 grams of any particular solute and we get a big container that we're going to dissolve it in, we'd put that into the container and then we'd get some water or any solvent, but presumably it'd be water, and we'd make it up to a line that was most likely 1 decimeter cubed on there. And so what we've got is we've got 40 grams in 1 decimeter cubed. And so we would say the concentration of the solution that we have made is 40 grams per decimeter cubed on there. If we were to represent that with just a space occupying, we could say that we have got 40 grams in that volume, and if that volume was 1 decimeter cubed, we can say we've got 40 grams per decimeter cubed. If we took that same volume, and this time we didn't put 40 grams in, we put 80 grams in instead, that same 1 decimeter cubed, this wouldn't be 40 grams per decimeter cubed, this would now be 40 grams per decimeter cubed on there. And if we just have a look at these 3 different sized shapes that I've prepared at the bottom, if we had this one being 100 grams, we'll put it inside, we've got 100 grams and the volume is 10 decimeters cubed, then the concentration is 100 divided by 10, which is 10 grams per decimeter cubed on there. This next one that I've drawn, let's make that 2 decimeter cubed in volume, not quite to scale, but let's say we had 60 grams in there, so we've not got as much solute, but the volume is much smaller. The concentration is 60 divided by 2, which is 30 grams per decimeter cubed. So even though it's a smaller volume, it's got a higher concentration because there's more mass per particular volume. And then last of all, let's put 40 grams into this one, and let's have this as only 1 decimeter cubed. And so this one has actually got the greatest concentration of all, even though it's the smallest. It's got 40 grams per cubic decimeter. So what we've been using without actually saying that we're using it is this very important relationship that is at the top here, and that is that the concentration of a particular solution in grams per cubic decimeter can be calculated if we take the mass of a solute in grams and divide it by the volume of a solution in cubic decimeters. So just 2 examples here of how to do that. So what is the concentration if there is 30 grams of solute in 0.2 decimeters cubed of water? And so the concentration is mass divided by volume, and the mass is 30 grams and the volume is 0.2 decimeters cubed, and so the answer is 30 divided by 0.2, which is 150, and we mustn't forget the units of grams per cubic decimeter on there. The second one is a little bit trickier because we've got 25 centimeters cubed of water, and really it's good to have everything in decimeters cubed, so we need to first convert that into decimeters cubed. So 0.025 cubic decimeters is that volume because we need to divide by 1000 to get there. And so then we've got the exact same situation as before. Concentration is mass divided by volume. The mass is 10, the volume is 0.025 cubic decimeters, and so when we plug that into a calculator we find it's 4.00 grams per decimeter cubed on there. It's good to have it to 3 significant figures as a good rule of thumb. We can use that same relationship that we've just been looking at to find out the mass of a solute in a particular solution. So for instance, we've got a question here that says, what is the mass of sodium hydroxide in 20 cubic centimetres of a 60 gram per decimeter cube solution of sodium hydroxide? So the first thing that we have to do is check the units of volume. Just like in the last example, the units are in centimetres cubed, so we need to convert 20 centimetres cubed into decimeters cubed, and we need to divide that by 1,000, so that is 0.02 cubic decimeters on there. And the second thing that we need to do is we need to rearrange the equation, because on this occasion we're not being asked for concentration, we're being asked for the mass of solute. Now, I prefer to rearrange things using algebra, and I encourage you to do that too, but I realise that lots of people find algebra very difficult, and so you like formula triangles. So a formula triangle for this, it needs to be quite a big triangle because we've got quite a few words to put into it. So we have mass of solute on the top, and then on the bottom we have the concentration in grams per decimeter cubed, and then we have volume last of all. And so remember how you use this, you cover up what you're looking for, and we're looking for mass of solute, and we're left with concentration multiplied by volume. So that's what we need to use in this situation here. So since concentration is mass divided by volume, therefore mass is concentration multiplied by volume, which we've got our concentration of 60 grams per decimeter cubed. We know our volume now is 0.02 decimeters cubed, so it's 60 multiplied by 0.02, which is 1.2 grams of solute. Let's move on now to look at concentration in moles per decimeter cubed. It's really similar to grams per decimeter cubed, and if you have a look at the equation, it's in the exact identical structure, which makes sense because concentration is an amount of substance per unit volume. And so the only difference is, instead of grams per decimeter cubed, we've now put moles per decimeter cubed. And instead of an amount of solute in grams, we've now got an amount of solute in moles. So in the exact same way as before, if we say that this has got a volume of 5 cubic decimeters and we've got 10 moles in that space, the concentration is 10 divided by 5, the moles divided by the volume, which is 2 moles per decimeter cubed. If we have a look at the second example, obviously the volume is smaller. Let's make that 1 cubic decimeter, and let's say there are 3 moles inside it. Well, this is really easy. Concentration is moles divided by volume, which is 3 divided by 1. So this is 3 moles per cubic decimeter on there. And the last example, let's say that this is 2 decimeters cubed of space and that we've got 4 moles in it. Then concentration is moles divided by volume, which is 4 divided by 2, which is 2 moles per cubic decimeter. If we have a look at this example at the bottom, this is more of an exam style question. What is the concentration in moles per cubic decimeter if 3 moles of salt are dissolved in 500 cubic centimetres of water? And so once again, the first thing that we have to do is address that issue that's in cubic centimetres, and so we need to divide that number by 1,000, and the volume is therefore 0.500 cubic decimetres on there. And then we just have to use the equation in the exact same format that it is at the top of this page, which is that concentration is moles divided by volume, because we've been told that there are 3 moles, and we've now calculated that the volume is 0.5, and so the answer to this is 3 divided by 0.5, which is 6 moles per cubic decimeter. This question is a little bit more complicated but uses the same equation, but there's an extra factor to weave into it. So what is the concentration in moles per cubic decimeter if 1.83 grams, there should be a G there, 1.83 grams of hydrochloric acid are dissolved in 0.25 decimeter cubed of water? So the first thing, let's just double check our volume. This time the volume has been nice. I've given it to you in cubic decimeters already, so no conversion needed there. Where I've been a bit mean is I haven't given you an amount of moles. I've given you a mass in grams. So our first thought is this needs to be converted into moles. And the way that we convert moles from mass is here. So moles equals mass divided by relative formula mass, which is the MR. Now the reason I've put this as step 2 is I know that we need to calculate the relative formula mass first, the MR. To do that, we need to add up the masses of all the atoms that are in HCl. And so we've got 1 hydrogen and we've got 1 chlorine in HCl. Hydrogen has got a relative atomic mass of 1. Chlorine has got a relative atomic mass of 35.5. And we just need to add those two together and we get 36.5 is the relative formula mass of hydrochloric acid, hydrogen chloride. So now we know the mass, because the mass was given to us in the question, 1.83 grams, and we know what the relative formula mass is because we've just calculated it, 36.5. And so now we can calculate moles by dividing mass by MR, and we get 0.0501 moles to 3 significant figures. And so now we can move on to step 3, which is the final step, which is to calculate the concentration. And the concentration is moles divided by volume, just like before. And so the moles, we've now got our moles value, 0.0501. The volume we were given in the question, 0.25. And so we get our final answer for our concentration as 0.204 moles per cubic decimeter. One final question then to have a look at. What is the mass of salt present in 0.600 cubic decimeters of salt water with a concentration of 0.450 moles per cubic decimeter? So let's quickly annotate this as if we were reading our exam question. We've got our volume and we've got our concentration. So the first thing that we need to do is we can do moles equals concentration times by volume, which is concentration 0.450 times by 0.600, which gives us a number of moles equal to 0.270 moles of salt. The relative molecular mass of salt, they would give you the formula, probably up here they'd say salt, NaCl up there. You wouldn't be expected to remember this. And so the MR of sodium chloride is 1 sodium, which is 23, and another chlorine, 35.5 on here, so just 1 sodium and 1 chlorine, because there's no numbers in that formula. And so that adds up to 58.5 units of relative formula mass are grams per mole, but I'm putting that in brackets because you don't need that for your GCSE course, and you don't need it for this question. And then the units of mass, just like moles equals mass over MR, just redrawing the triangle that you will have remembered from a previous video. The mass, we cover up what we're interested in, and we cover up mass on here, and mass is moles times by MR. And moles we've calculated in step 1 was 0.270, MR we've just calculated is 58.5, and then we get a final answer of 15.8 grams of salt to 3 significant figures. Remember to read the question carefully, they'll tell you the number of significant figures they want you to use. Now we've got 2 units for concentration, so it's important that you can change between those 2 units if they give you the command. So to do that, let me show you a situation here where we've got sodium hydroxide. We've got 1 mole of sodium hydroxide in 1 decimeter cubed, and so the concentration is 1 mole per cubic decimeter. Now, if we took that same situation and instead of using moles, we got rid of moles and we put that as a mass instead. Now, let's put that as 40 grams. And so we know that we can change the units of concentration. It's not going to be 1 mole per decimeter cubed anymore. It's going to be 40 grams per decimeter cubed on there. Now what I know, and the reason that I made these numbers up, is that the MR of sodium hydroxide is 23 for the sodium, 16 for the oxygen and 1 for the hydrogen. So we add all of those three numbers together and we get 40 grams per mole. And so the reason I chose these numbers is that I knew that these two concentrations were equivalent. And so for sodium hydroxide, because the MR of sodium hydroxide is 40, 1 mole per cubic decimeter will have the exact same concentration as 40 grams per cubic decimeter. And in fact, if we just said that differently, if we had 1 cubic decimeter of sodium hydroxide, we would have 40 grams of sodium hydroxide, which is the equivalent of 1 mole. Now, what you need to be able to do is you need to be able to convert between the two. And so what's really important is that you remember this relationship on here. The concentration of a solution in grams per cubic decimeter is the concentration of a solution in moles per cubic decimeter simply multiplied by the relative formula mass, the MR on there. And that makes sense if you consider the units. Grams per decimeter cubed is moles per decimeter cubed multiplied by grams per mole on there. The moles will cancel out and we'll be left with grams per decimeter cubed. Let's just consider one example of that. So if we had the concentration of sulfuric acid, H2SO4, is 0.0312 moles per cubic decimeter, what is the concentration in grams per decimeter cubed? So we know the concentration in moles per decimeter cubed, and so our two steps, the first step is to calculate the MR of sulfuric acid, and the MR is 1 plus 1 for those two hydrogen in H2SO4. The S is 32, the 4 oxygen is 4 lots of 16. And when you add all of those things together, we should get 98. And so the second and final step is to work out what the concentration is in grams per cubic decimeter. And remember, to do that, we need to take the concentration in moles per cubic decimeter and multiply it by the MR. And so we've got 0.0312 times by the MR, which is 98, which, when we work that out to three significant figures, is 3.06 grams per cubic decimeter. And so just to show it you in the other orientation, if we weren't trying to work out concentration in grams per decimeter cubed, we were trying to work out the concentration in moles per decimeter cubed, we would rearrange it and instead divide the concentration in grams per decimeter cubed by the MR. And so in an example, if we said we've got 17.1 grams per decimeter cubed, and that is the concentration of a solution of potassium hydroxide, what is the concentration in moles per decimeter cubed? And so the two steps are slightly different, but the same first step. Our first step is to calculate the MR of potassium hydroxide. So it's 39 for the potassium, 16 for the oxygen, and 1 for the hydrogen, which gives us a total of 56. And then the final step is to use it in the organisation that we had up at the top. So the concentration in moles per decimeter cubed is in grams per decimeter cubed, which we've got 17.1 grams per decimeter cubed. Divide it by the MR, which is 56, and that gives us 0.305 moles per cubic decimeter. The final thing I want to look at in this video is something called uncertainty or uncertainties. All measurements have some uncertainty to them, and experiments will often be repeated, and then once you've got those repeated values, you will calculate a mean from them. So let's imagine that we were investigating the volume of acid needed to fully neutralise a particular base, and we've got our data here in a table. So obviously it's been repeated 5 times. It's good practice to do at least 3. We've got 5 here, and then the volume was calculated in each of these cases. And so what you would do first of all is you'd calculate a mean for these 5 different repeat values. Now, to calculate a mean, you add up all the values and then you divide it by the number of values that you're trying to take a mean of. And so what we would have here is we'd have 20.2 plus 20 plus 19.9 plus 20.3 plus 20.1, and then we divide all of those numbers by 5 and we'd get a mean value of 20.1. Cubic centimetres, must always remember the units. Now, another quantity to do with an investigation is the range, and the range is the difference between the largest and the smallest. So it's the largest take away the smallest. So in this case on here, that's 20.3 was our largest measurement and our smallest was 19.9. So the range is 0.4 cubic centimetres. This new phrase uncertainty, the uncertainty, it's a measure of sort of how far out your values could be, and that's taken to be half the range. And what that means is if our range was 0.4, we need to divide that by 2, and that's obviously 0.2 cubic centimetres. But what the uncertainty means is that we could be slightly higher than we think by 0.2, or we could be slightly lower than we think by 0.2, which is why we've got this plus and the minus here for slightly higher than we think and slightly lower than we think. And so when we quote our actual answer, our answer is the mean value plus or minus the uncertainty. And so for our situation here, our answer was 20.1, our uncertainty was 0.2, and then that's in the units of cubic centimetres. And so we think our answer was 20.1, but it could have been as high as 20.3. That's when we add the 0.2 on, or it could have been as low as 19.9, which is when we take away the 0.2. One last example of uncertainty for the same experiment, so I'm not introducing it again, and we've got the same 5 repeats, but this time we've got different numbers. And the reason that I've included different numbers is because one of the numbers is odd. It does not fit the pattern, and we call that an anomaly. So an anomaly is an odd result. Sometimes we call it an outlier, but in science we call it an anomaly in GCSE chemistry. Now, the crucial thing about anomalies is that you do not include them in your mean calculation, because if you do, it will make the mean too high or too low. So we ignore it. We acknowledge that we did it, and we acknowledge that it's there but slightly wrong. And so when we calculate the mean, we use the other 4 values, 19.8 plus 20 plus 20.6 plus 20.4. So those are our 4 numbers that we're using. And then we divide it by 4 because we're only using 4 numbers, and we therefore get an answer of 20.2. If we'd used the 10, that number would have been way too small because the 10 would have dropped our mean down. So we had our anomaly, which we leave out of the calculation. So the anomaly we leave out of the mean. And just in case you come across a different form of the word anomaly, the plural of anomaly is anomalies, like that. So the significance now, we've got our mean value of 20.2 cubic centimetres. We can calculate the range in exactly the same way as before. The range is the largest, which is 20.6 for here. Take away the smallest, which is 19.8, which gives us a range this time of 0.8 cubic centimetres. The uncertainty is half of our range, which is 0.8, which is plus or minus 0.4 cubic centimetres. So this time, whoever this person is who'd done this experiment got a very similar volume of 20.2 cubic centimetres, but because their range was greater, their uncertainty is greater as well. and so their uncertainty is plus or minus 0.4 cubic centimetres, which reflects the fact that this person could have got a result of 20.6 by adding that 0.4 on, and their lowest result could have been 19.8. Okay, we'll leave it there. Thank you for listening. I hope it's been useful, and we'll see you again soon.